We start off the day with a lecture by Tudor Dimofte from University of California at Davis. The title of his course is Higher Algebra in SUSY QFT. I think Tudor will tell the individual titles for the talks.
Thanks very much. There's a general theme going through these three lectures. In the last few decades, there's been increasing effort to describe topological quantum field theory mathematically. This was initiated in the early 90s by Atiyah and Siegel. Siegel tried to axiomatize conformal field theory, and then Atiyah wrote down axioms inspired by that for topological quantum field theory, involving assigning vector spaces to d-1 manifolds and numbers to d-manifolds, and having some functor from a cobordism category to vector spaces. Since then, this approach has been generalized in many ways. In particular, looking at extended operators or extended structure. Things like extended operators, manifolds with corners, and so on, led to the use, and I should really say the development, of higher categories. Also, not all of the topological quantum field theories one encounters in physics are topological on the nose. Many of them come from, say, twists of a supersymmetric theory. One finds Witten-type or cohomological TQFTs where only the homology is actually topological. And the mathematical treatment of those involves derived geometry. Or what's known as higher algebra. There are many, many names to associate to these developments. Again, it has spanned several decades. A very few to mention are Kontsevich, Lurie, and Costello. Also, as far as derived geometry in the context of physics goes, Tony Pantev and collaborators have done quite a lot developing that. There have been many successes, even purely mathematically, of this formal approach, including things like formulating and then proving the cobordism hypothesis, which is not something I'm going to talk about, but has been a main focus in this line of work. Unfortunately, some of these mathematical developments have gotten extremely abstract and difficult to parse difficult to parse from the viewpoint of a standard physicist. There are lots of very fancy statements coming out of math that don't have an obvious role in at least what I think of as a quantum field theory. In some upcoming papers, a few collaborators and I try to take some central concepts from the mathematics that haven't yet found a home in physics. And we actually try to apply these to some of my favorite examples of TQFTs, namely twists of supersymmetric field theories and supersymmetric gauge theories. For physics, this has actually led to the discovery, maybe. It's led to the realization that there's actually some fundamental structure that was never appreciated in supersymmetric theories. For mathematics, it provides a list of examples in a field that is very, very poor in examples so far. And in fact, if I get to the end of the talk, I'll start mentioning higher structures in categories or extended categories of extended operators. These things just exist in a supersymmetric quantum field theory, or in a twist of a supersymmetric quantum field theory. But very few, if any, examples are actually known on the mathematical side. So one can write down axioms and proofs and so on, but it's hard to verify anything. Hard to see how things are actually supposed to work. Right. So the talk today is about higher products in operator algebras. On Thursday, I want to say some things about gauge theories, and in particular the simplest examples of gauge theories, gauged quantum mechanics. And then build up to higher dimensions from there. And I should say, so these two talks are based on work with Chris Beam, David Ben-Zvi, Matt Bullimore, and Andy Knightsky. The talk on Friday is going to discuss some fancier applications of these ideas in the context of 3D n equals 4 gauge theory. These theories have interesting Higgs and Coulomb branches of vacua. The Coulomb branch very recently got a full mathematical description by Braverman, Finkelberg, and Nakajima. And there are all sorts of cool representation theoretic structures coming out of this. I find the sort of fundamental structure I will describe in the first two lectures to be extremely helpful in analyzing some of the geometry that comes from 3D n equals 4. And so I'll talk about that on Friday. Okay. So this lecture is going, well, this and the lecture on Thursday are both going to be super low level. Also, feel free to just interrupt at any point and stop me. I am going to assume a bit of familiarity with quantum field theory. So the focus of this talk is going to be supersymmetric field theories in d dimensions. that admit a topological twist. I mean something very specific by that, which is not exactly the way twists were first described. So as a supersymmetric theory has a superalgebra of symmetries in flat space, in addition to translations and rotations, which are symmetries of the theory. There are some odd symmetries that relate bosons and fermions. So there are some odd generators in the symmetry algebra. I want there to exist a distinguished odd generator that squares to 0 and will act as a differential on everything in sight. So Q is some element in the symmetry algebra. Q commutes with translations. And I will also require that there exist some more odd generators, some more odd elements in the supersymmetry algebra that trivialize the translations, that make the translations Q-exact. These are also in there, and this is true in any twist of a supersymmetric theory that we know of. Okay. I will also work. We'll keep things extremely simple. So I want to work on flat space. So all of the structure I will talk about is really purely local, and it makes sense to analyze it in a tiny patch of space-time that effectively looks like R to the D. Yeah. Gone back and forth on this. Sure. Yeah, exactly. And so if you have that, then so you write this in terms of a supercurrent and the stress tensor, and yeah. So the paper on this is hopefully coming out in the next week or so, even though we've been working on this stuff for almost 2 years now. It's not going to sound very complicated here, but actually pinning down like the precise properties one needs or should postulate is tricky. I don't think I will need to use a stress tensor in here, but yeah. I don't. I may not be, but these structures I will talk about are local. So it doesn't. In other words, it doesn't matter whether I am or not. If I'm on some curved space, there's still operator algebras that exist in a tiny patch. So in such a theory, one can talk about local operators. This is a vector space. Usually in QFT, one thinks of local operators as things inserted at a point that one can compute correlation functions of. It is useful to enlarge that notion very slightly and say that this is going to be any sort of collection of insertions that are localized within a ball. And in the physical theory, this space depends on the size of the ball. So the picture is like this. Here's the ball. And there can be all sorts of stuff inside. Again, this is a vector space. Now, our differential Q acts on everything in sight. In particular, it acts on this vector space. And in the topologically twisted theory, what one is usually interested in is not this gigantic space of all operators within a ball, but rather its cohomology. So A is going to be the Q cohomology of ops. And these are what's known as topological operators. Now, A is independent of the size of this ball. The way to see that is actually a consequence of what I'm going to say next. So this is independent. B. Moreover, A is an algebra, which is why it's called A. It's associative in dimension 1 and commutative in dimension 2 or higher. All right, why is it an algebra? Roughly because I can collide local operators. And in Q cohomology, the OPEs are non-singular. And so it makes sense to take two local operators and smash them together and build another local operator. We'll call that the primary product. Actually, before I write down what it is, let me recall a very useful feature of the Q cohomology of the operator algebra, which is why it's called topological in the first place. This fact that Q, well, the fact that translations are Q-exact implies that correlation functions of local operators are independent of insertion points. If I'm working in this generality and thinking about local operators as things inserted within a ball, the ball has some center. Let's talk about some local operator O centered at x, or you can think of this as literally just a single field evaluated at x. So the main property here, a very classic one, is that for Q closed, local operators, as many as I want, correlation functions, are independent of the insertion points. Yes. So the depends how you're viewing this. So if you're coming at this perspective as a physicist, then you know what it means to insert things at points or other extended loci in space-time, and then I can say local operators are just all collections of things that one can insert within a ball, and I choose some ball centered at x. If you're a mathematician, and then it's more useful to say that this is the vector space of states that the theory assigns to the boundary of this ball in radial quantization. And that's a description that doesn't require me to talk about inserting things, and I should have said that. So this is the vector space one gets upon quantization of the theory. Radial quantization of the theory. On a d-1 sphere. Yes, I'm saying that the radius, that there is some flat connection. I'm going to say, this is where you get, I get into things that take forever to discuss. So the Q cohomology of this vector space is independent of the size of the sphere, is the statement. Physically, it is certainly not independent. It matters what the radius is. But because of this property I'm about to review, one can contract or expand everything at will while keeping the Q cohomology class fixed. Yeah. I think the cleanest, absolutely, the cleanest way to do that is by using exactness of the stress tensor. Yes. Yeah. Yeah. Yes. Yes, sorry, if it, but like extended but not infinite. So I could have a little loop that's curled up in here. And anything, yes. And if this is phrased as states in radial quantization, then it's clear that you can do whatever you want inside the ball. Okay. That is sometimes true. That's true when there's a Hilbert space involved. They're observables in the sense that it makes sense to compute correlation functions in any given vacuum. Sure. Sorry. So yes, they are observables exactly like this. Definition. Yeah, let me not. if I have, what do I want to say? I get to this description in terms of states by just removing the ball, and saying, and anything I do inside this ball should translate to something that's happening on its boundary in radial quantization of the theory. It has to be so. This is a standard thing called a state operator correspondence in a conformal theory. I'm not assuming I have a conformal theory, and so what you should think about is state operator correspondence. And yeah. So, I mean, yes, I could say those words, and you will see aspects of factorization algebra coming in, but yeah, but I'm not going to. Okay. No, I do assume that that there's a Z2 grading. By fermion number. That's all you need. I mean, it may or may not be realized in the actual theory. There are lots of cases where it's broken. In nice examples, yes, there is some R symmetry, and then there are selection rules, and then this Z2 grading is actually a Z grading, and saying that everything is graded is the same as saying selection rule. Sure. Yeah. Okay. I'm going to finish this for people who haven't seen it before, or as a review for all of us who have. So if there are operators that are killed by Q, correlation functions are independent of the positions. Yes. Yes. I am not. No. It may not act on the fields. Right? It depends on the field content and interactions, and it's broken by instantons. It may be anomalous. No. That is independent of curving, of working on curved space. So this sort of argument, everything I'm about to say makes sense even in theories where the R symmetry is anomalous, so that putting an uncurved space is impossible. This is still fine. Okay, so argument. If one infinitesimally translates the position of one of the variables of one of the local operators, that's an application up to an I that I am going to sort of ignore for the talk. That's an application of p mu on one of the operators, and then using the equation that says p mu is q exact, that's q of q mu of O1, and then a bunch of other operators. And because all of the other operators are closed, that's Q of the entire product sitting here. And then one invokes the fact that Q is a symmetry of the theory. Being a symmetry of the theory precisely means that correlation functions of the infinitesimal symmetry generator acting on anything is 0 by an integration by parts in the path integral, if you want. So correlation functions are independent, at least infinitesimally, of the insertion points. One thing I should also say, which again is usually understood in physics, though not spelled out, the only thing one ever cares about are correlation functions. So all equalities one writes down in an operator algebra are meant to be understood inside correlation functions. All limits are sort of weak limits. They're limits that hold in expectation value. Okay, move on. So this allows one to talk about a product. Informally, what one wants to say is that the product of two local operators is the limit in this weak correlation function sense I just mentioned of the collection of the two operators. In terms of spheres, a better picture to think about is that of including two small spheres into a big sphere. So putting two small spheres carrying O1 and O2 into a bigger sphere defines the product O1, O2. And I should emphasize the product, it's only the cohomology class of the product that's well defined. Playing these games, taking limits and keeping everything constant, or including two spheres inside a bigger one, and then shrinking the big one back down to normal size. All of these games involve working modulo Q-exact quantities. So if I'm careful about it, it's only the cohomology class of this thing that is well defined. Sorry, yeah. I mean, because I don't want to have to define some extra things that I don't need. But this is it, yes. Okay. So in one dimension, this product is associative. There are two ways. There are two ways to collide operators, and they're inequivalent. There's no continuous way to deform the left configuration to the right configuration. I am not allowed to put operators right on top of each other. The topological way to say that is that the configuration space of 2 points on the real line, namely r times r minus the diagonal, which is homotopic to S0, has two connected components. And these are the two different ways to form a product. In higher dimensions, I can smoothly move operators around each other. And swap their positions if I want. The product in higher dimensions is graded. Commutative. So naively, it's just commutative. Graded comes in because when writing down something like a correlation function, you actually have to choose an order for these operators. And if you're careful about it, that Z2 fermion number grading plays a role. So what one finds is that O1, O2 is -1 to the fermion number of O1, fermion number of O2, O2, O1. The fancy topological way to say this is that the configuration space of 2 points in R to the D, which is homotopic to a D-1 sphere. This is the sphere of relative positions of one operator with respect to the other, is connected. Okay. So this is all old stuff, maybe said in some fancier way involving configuration space. The point of this talk is that this is not it. Yeah, and everything is. Yeah. So I do have Q closed. On the other hand, correlators of Q exact things are automatically 0. So everything's a cohomology class. Yeah, absolutely. So I should, if I were careful about this, there would be brackets around everything in sight. Okay, so right, so there are operator algebras and topological theories. This is something we have known for a very, very long time. The point is that that's not everything. What else can you do? Well, the fact that commutativity in higher dimensions doesn't hold on the nose, but only holds modulo Q exact things, actually allows you to construct a secondary operation. And just write it here. It endows A with the structure of a graded Lie algebra. Or graded Poisson algebra is maybe a better thing to say. And so this is one of these statements that appeared in the mathematical treatment that took a bit of thinking to write in down-to-earth physical terms. Where does a Lie bracket or a Poisson bracket come from? There's another way to form a product of two operators that involves topological descent. So this was introduced by Witten in the context of Donaldson theory. The idea is that given a Q closed, local operator O, one can construct a one-form operator, O1, by using the fact that translations are Q exact. So, sorry, best way to say this. So we know that infinitesimal translations of O are Q of something. In fact, they're Q of Q mu of O. I can write that as an exterior derivative instead in space-time and say d of O is Q of Q mu of O dx mu. And this this one form here is called the first descendant of the operator O. What I just wrote down is the descent equation. Now, the descendant itself is not Q closed. But its integral on any one cycle in space-time is. And that's just an application of Stokes' theorem. So applying Q to this is the same thing as applying the exterior derivative on O itself, and essentially that's a total derivative. By Stokes' theorem, that's the integral on the boundary of gamma of O, and if gamma is a closed one cycle, that's 0. It's a one cycle. Moreover, the cohomology class of this integrated operator doesn't depend on the precise form of gamma, it just depends on its homology class in spacetime. So this was used to construct extended operators in Donaldson theory. We can use it in a much simpler way here. I made it up. You don't need anything to write this down. So this is just a definition of O1. Yeah, I could. Let me just write it like this. So O1 is just defined as Q mu of O dx mu. OK can iterate the process and form a k-fold descendant is what I get by applying Q mu k times and is a k form on space-time, and the integrals of these k forms on closed k cycles are all topological operators. They're all Q closed. Is that good? Right. Cool. So now we can define a secondary product of two local operators, O1 and O2, which I'll write as a bracket. This is going to be obtained by integrating the d minus first descendant of O1 around a sphere surrounding O2. So the picture is like this. Here's O2. It's sitting at some point. Surround that point with a d minus 1 sphere and integrate the descendant of O1 around that sphere. This is this entire configuration is, again, a local operator. It's contained within some ball. Moreover, the configuration is topologically non-trivial. Since I'm not allowed to let the actual positions of operators coincide, I can't just move O2 outside of the sphere. So that defines a new way to take the product, and one can check. So if O1 and O2 are Q closed, then this again is Q closed. This is in cohomology. So this endows the operator algebra with another product operation. And this product has some really nice properties. First, in terms of fermion number, I will note that since a d minus first descendant was involved, the fermion number has changed d minus 1 times. So the secondary product has degree. If things are z-graded, it's 1 minus d. Otherwise, it's just even or odd, depending on the parity of 1 minus d. It's graded symmetric. In the sense that the bracket of O1, O2 is minus 1 to the product of the fermion numbers plus the dimension. O2, O1. And the dimension of space-time comes into whether this is even or odd. It's a derivation with respect to the primary product in each slot. And it satisfies a graded Jacobi identity. These are all really elementary properties. They are not obvious the way I've defined the secondary product here. They become much more obvious with a slightly enlarged perspective on the secondary product. A nicer way to think about descent is not on single local operators, but rather on collections of local operators. If I consider some product of n local operators, the quote-unquote position of this product is a point in configuration space. It's a point in the configuration space of n points in R to the d. And then one can run descent on configuration space by simultaneously taking variations with respect to all of the x's. So the first I can write down descent equations, but instead I'm just going to write down how to solve them. The first descendant of this entire configuration is obtained by applying Q mu to all of the different operators in the product. So it's Q mu O1 dx1. I should probably have put these indices downstairs. Sorry. dx1 mu, and then the rest of them. And then I just form a linear combination. I act with Q mu as a derivation, and act independently on each of the O's. There's a sum of n terms ending in Q mu applied to On dxn mu. Okay. And it should all be graded, so these are pluses or minuses depending on fermion number. Yes. So this is now not a one form on space-time, but rather a one form on configuration space. By continuing to apply Q mu, one can build K-form descendants that are K-forms on configuration space. And the natural thing to pair K-forms on configuration space with are cycles on configuration space. So we'll pair this with a K-cycle. And choosing any K-cycle whatsoever and integrating this product descendant on it defines a product operation. So every K-cycle gamma in configuration space defines a product operation on the algebra. Now, that suddenly seems much more general than what we began talking about 40 minutes ago. It is, in fact, actually not that bad. So first I should say, algebras whose products are controlled by homology classes in configuration space are called En algebras, or in this case, it's the dimension of space-time that comes in. This thing is called an Ed algebra. So A is an Ed algebra. Sorry? If in making the statement that it's an Ed algebra, I should be working at the chain level. I agree. Well, like I said, so I'm translating things that in math are extremely well known. But yes, I agree. So ED exists at the chain level. It encompasses like L infinity algebras or homotopy Lie algebras that show up in physics. Here, I actually only care about about A as cohomology classes. And there, I can invoke a nice theorem. Oh, I should probably write it down. Gamma of n operators is the integral around gamma of the kth descendant as a form on configuration space. It's an operator. It's a local operator. I mean, if I throw this into any correlation function, it gives me a number. But when I think of throwing things into correlation functions, I'm allowing arbitrary other insertions away. So I'm saying this is equivalent to just some single local operator, and that's the result of this operation. It is not. Let me say that right now. Configuration space is not contractible, and that's where the cycles live. Here in this operation, I did integration on an SD-1, but the SD-1 was not allowed to shrink because there was this other insertion of O2 in the middle. Correlation functions, like these, all of the topological properties of correlation functions, the fact that they're non-singular, hold as long as you do not place two operators at the same point. Yes, exactly. Yeah, so, so math theorem. The cohomology of an ED algebra, so really, I'm sorry, I should have just written ops here. And the cohomology of an ED algebra, it's an algebra whose products, it's an algebra that has a product for every cycle in configuration space. It is, sorry, no, it's exactly that. I just didn't say it clearly. Yes. That's right. So these are all fuzzy.
Yeah, and the difference here is if I take that and O2, which is just a local operator, right, there are two choices. They're both supported inside the ball, but they could be linked or unlinked. And the unlinked one gives you the usual product of those two operators, and the linked one gives you the secondary product.
Yeah, exactly.
Right. But now we also have other extended operators. We have OKs for various Ks, and they can be linked if K1 and K2 are appropriate in arbitrarily complicated ways, and several lectures.
Absolutely. So yeah. Let me try to clarify some of that. So first, the cohomology. Of an ED algebra, this is algebra theorem, is what's called the PD algebra, which just means graded Poisson. In other words, working with cohomology classes, working with topological algebra A, all of the fancy products are generated by the primary one and the secondary one. That's all one actually needs to think about in cohomology, which simplifies the story considerably. Then we just have to understand the secondary product. And then looking at the definition of these products, they didn't depend on the precise form of a cycle in configuration space. They depended on its homology class. And so there are lots of ways, as Jacques said, there are lots of ways to link two descendant operators. But the result of linking them only depends on a homology class in configuration space. If we take that case, d equals 3, well, I don't want to say k equals 1. Let's just consider d equals 3. So the original definition of the secondary product, actually, let me say what configuration space is. So the configuration space of 2 points in R3 is homotopy equivalent to S2. 2 points in R to the D gives us SD minus 1, where this is the sphere of directions pointing from one operator to the other. So this has two homology classes. So the homology is generated by a point class of degree 0 and the class of S2 itself of degree 2. And if I'm working modulo 2, then these are both even degree. The point class defines the ordinary product. The class of S2 defines the bracket. Now, it doesn't matter exactly which cycle I use as long as it's in the homology class of the S2. So in three dimensions, I can define, like I did initially, I can define the bracket of O1 and O2 by integrating the second descendant of O1 around O2. But that's equivalent to integrating the first descendant of each of them on a hop link. So the hop link defines a cycle in configuration space that's topologically a torus, but it's in the same homology class as the S2. In fact, the linking number of any two-component link is literally the number of, it's the proportionality constant between the homology class of that cycle and the S2. In other words, integrating the first descendant of each of them around a two-component link it just gives me the linking number of that link times the secondary product. Yes, thank you. Is that... I don't know. I have not seen one. Yes, absolutely. If you have genuine line operators around, then yes, absolutely. Okay, so I hope that's let some of the dust settle. Well, so that's why I wanted to throw ops in here. But yeah, anyway, let me. Yes. Yeah. The upshot. There are many levels of structure here. One of the simple upshots is that working with cohomology classes, one gets two products. Now, let me, before I run out of time, let me give you some examples of this. So in 2 dimensions, the bracket is, and the bracket has fermion number 1. It's odd. It pairs bosons and fermions. And it's already super well known in physics, or at least it was in the 90s. So this showed up in constructions of string field theory. In particular, closed string field theory, and work of Zweibach and Witten. It was described in almost exactly the same form I wrote down now by Getzler following work of Lien and Zuckerman. So it was well known. It was well known back then. The simplest example that I can possibly describe is in the B model. Right, so I should also say, like, these sorts of operations of taking a descendant of one operator and integrating it around another are really familiar in CFT. And so the two-dimensional pictures are nothing new. I'm just doing them in arbitrary topological theories. So in the B model, with Kähler target, the algebra of topological operators is known as polyvector fields on X. So it's del bar cohomology of X valued in wedge powers of the holomorphic tangent bundle. And in particular, this includes holomorphic functions and holomorphic vector fields. The primary product is just the product of functions, or the wedge of vector fields. But the secondary product is what's known as the Schouten-Nijenhuis bracket. It is the natural extension of the Lie bracket of vector fields. Now, you know that if you take a Lie bracket of two vector fields, you get another vector field. Vector fields are odd. They're fermionic in this algebra. And indeed, so fermion paired with fermion gives you another fermion. That's the property of the bracket itself being odd. Or if you act with a vector field on a function, you get a number, or you get another function. And again, is consistent with that bracket being odd. Let's do a slightly less trivial example. Let me just finish up with this, and then I'll continue tomorrow. So in d equals 3, a famous example of a twisted topological theory is Rosansky-Witten theory. So this is a twist of a 3D n equals 4 sigma model to a space X that, if you want to write it as a 3D n equals 4 theory, should be hyperkähler. From the perspective of the twist, you just need this to be complex symplectic. In particular, it's equipped with a holomorphic symplectic form. Now, geometrically, the holomorphic symplectic form takes the algebra, or it turns the algebra of holomorphic functions on X into a Poisson algebra. And so there's an obvious Poisson algebra sitting around. The really cool thing is that that Poisson bracket is actually recovered as the secondary product in the TQFT. And so one can actually, one can compute the symplectic structure physically by applying this descent operation. So here, local operators correspond to del Boca homology of X. In particular, this includes holomorphic functions on X, the chiral ring of the 3D theory, and the secondary bracket of functions, the secondary product, is, by a non-trivial calculation, is the Poisson bracket. One very cool consequence of that is an immediate non-renormalization theorem. This tells you that the holomorphic symplectic structure is a topological property of the theory. It's never going to be renormalized. Another cool consequence that I'll talk about tomorrow is a new perspective on omega background and quantization. That, again, has the fact that turning on an omega background quantizes the algebra of operators is really well known, but this gives a nice topological way to look at that. Thanks. Sorry? In which? So associativity comes from manipulations in configuration space. So you take a product of 3 operators. So the question is whether some higher product is invariant under exchanges of position or exchanges of orders. And that all translates to moving a cycle around in configuration space and showing that 2 cycles are in the same homology class. That's the short answer. So the algebra is associative in 1 dimension. It's actually commutative in higher. But it's still, I mean, it's commutative. It's graded commutative in 3D. The Jacobi identity is something really non-trivial for the bracket, and that's proved by taking a product of 3 and. Yes, sorry. Oh, sorry, of the secondary, I'm so sorry, associativity of the secondary product. Yeah. So that's an identity in homology of the configuration space of 3 points. I mean, it will take some time to write down the details, but it's a straightforward. You look at what the bracket, like you look at 2 nested brackets and see what cycle that corresponds to. It's. I mean, it's an arbitrary D. It involves a D minus first descendant and another D minus first descendant. And so it's something in 2D minus 2 dimensions, but it's actually not hard to see what the manipulation is. No, I'm happy to talk about that later. Again, I can talk to you about that later. Yeah. I mean, it all has to do, I mean, yes, this is important in the BCFV description, but that's another story. Let me finish the talk.
So you mentioned at the beginning the notion of extended TQFTs, where you have line operators, surface operators, and so on, at least in the physicist language. But one of the things you kind of showed us here is that, for instance, in the simplest of these cohomological TQFTs, sure, there are line operators and surface operators and whatnot, which are just these descendants. But they sort of have a stupid feature, namely that their products are all determined from your primary and secondary product of the local operators. So in some sense, they're not encoding anything new. Does that give some kind of diagnostic on, like, when extended TQFTs are actually interesting, or just repackaging of the sort of data of the unextended theory? Okay. This was a very vague question, I apologize, but I'd like to distinguish between the extended TQFTs, which have genuinely new products for the extended operators, and those which have these, I hesitate to call it stupid because it's very beautiful, but this thing which is entirely determined by this.
No, I know exactly what you mean. So there's several ways I think about that, but I don't think I've hit on exactly the right characterization yet. So to me, it's sort of a notion of light versus heavy. So honest extended operators are in the path integral are exponentials of things. They're like Wilson lines, whereas these are polynomials. So in some sense where there's a coupling constant around or something like that, there's a light versus heavy. The actual extended operators cause heavier singularities in the equations of motion. That's not a really good, that's not an invariant characterization. A slightly better one is that honest extended operators have their own k-dimensional or TQF or k-dimensional QFTs living on them, and there are local operators bound to the extended operators that are non-trivial, that don't exist elsewhere in the bulk, and that is actually a sharp distinction between these descendant guys and honest extended operators. So these form a category, but it's a really stupid category. You can't have. I mean, there are no HOMs, there are no interfaces. But I have not put my finger on just exactly the perfect way to say that. Sorry, I will say one more thing. This entire game of higher products works in extended TQFT. Sure. So the generalization of the statement about EN algebras is that n extended operators, the genuine guys, form an E d minus n monoidal n category. And that's a very efficient way to say braided tensor. for line operators in D equals 3. And there are secondary products involving all of these guys, and that's a really cool thing that has not been much explored, that I also have not had time to talk about. Sorry. Yeah. It is, and it works the same way. I mean, yeah. If you start out with a physical theory, yes. If you start out with a supersymmetric theory, then yes, it does. It's the, I mean, in general, if you write down a cohomological TQFT, I'm not sure it actually needs to be there. You can still solve the descent equations. It's just that the solutions won't be canonical.
Okay, if not, we'll thank Tudor again.